Hello, so this is section 3.3 and the topic today is the factor theorem. So before we start on the new topic, we're just going to look at a review question, should recap on some of the things we looked at in the last section. So here we're finding the remainder when we have this polynomial here divided by x minus 2. Now, from the last section, we looked at 3 ways where we could figure out a remainder when dividing polynomials by a binomial. First was long division. And then from long division, we looked at a second method, which was called synthetic division. And thirdly, the third way was something called remainder theorem. Something about that didn't spell right. Theorem. Okay. So out of the 3 ways, all 3 will help you figure out the remainder. I'm going to pick the remainder theorem for this particular example. So for the remainder theorem, you'll look at that binomial. Remember, this is x minus k. So we know k equals to 2. Now that we have the k value, we're just going to stick it into the polynomial and see what value we get. So 2 into where x was. So we 3, 2 to the power 2 minus 8, 2 minus 12. Now from here, 2 times 8 is 16, 3 times 4 is 12, minus 16 minus 12. When we put all these numbers together, 16s cancel out, 12s cancel out, we're left with 0. So this here, remember, the number we get is our remainder. So when the remainder is 0, in this particular case, the binomial x minus 2 is what we call a factor. Because since there is no remainder, it means that the x minus 2 was able to divide completely into our polynomial. And when you could divide something completely, it's what we call a factor. So the binomial x minus k is a factor of the polynomial function if when you put in that k value, your output is 0. And this is what we call the factor theorem. So when you think about it, the factor theorem really is just an extension from the remainder theorem. So from the remainder theorem, we know the binomial, we set it to x minus k. When we have that k value, we stick it in and we find the remainder. The factor theorem just states, well, if you put in some k value and you see that the remainder is 0, then you know that x minus k is indeed a factor. So it's kind of an extension on that idea. So the big idea here. So the possible factors of a polynomial with leading coefficient of 1, remember leading coefficient is the coefficient in front of the highest exponent, are found by testing the integers which divide into the constant term. So constant term is that value right there where it's not linked to any variable, okay? And from here, we have something called the integral 0 theorem. So given some polynomial function has an integral 0 of x minus k, so there's some 0, which is x minus k, then k is a factor of the constant term of the polynomial. So if we're trying to look for some factor, then we know that that k value is going to be a factor of the constant term. So right now, when we look at this question, so we want to factor fully this polynomial expression. Step 1, look for possible integers which divide into 8. So 8 could be 1 and 8, could be 2 and 4. Now remember, since we are looking at when we're dividing 8, it could be plus or minus for all of these values. So these are the 4 numbers plus or minus that we can possibly test if it's going to work as a factor or not. Step 2. Find an integer that gives the expression a remainder of 0. So here is where we're going to use that remainder theorem that we tested last time. So I'm just going to start with testing the k equals to 1. Okay, so I'm going to put 1 into this polynomial and see how it goes. So if I put 1 in here, plus 5, 1, 2, plus 2, 1, minus 8. So here's 1 plus 5 plus 2 minus 8. Well, this equals 0. All right, so since it equals to 0, then we know that x minus k is a factor. Now, x minus k specifically here is x minus 1 is a factor. All right, now that we know that x minus 1 is a factor, we're going to figure out what are the other parts through long division or synthetic division. You can pick either or, whichever floats your boat that makes you more comfortable. I'm going to pick synthetic division myself here, okay? So remember, in synthetic division, we have our L bracket. Gonna put that the value right there on the outside, so -1 goes out here, and the coefficients will sit nicely in the bracket, which is 1, 5, 2, and -8. So let's pull down that first number, 1, multiply the 2, which is -1, subtract 6, multiply -6, subtract, which will be 8, multiply -8, subtract 0. So when you go through this process, since you know you found a factor, then you already know for a fact that here you should get a remainder of 0. If you still end up with a number as a remainder, then you either have made a mistake in your division or you have made a mistake in your last step in finding the factor. Okay, so remainder should be 0 once you found a factor. All right, so again, what do these numbers mean? Well, it means that we have that our polynomial is equivalent to x minus 1 times the stuff we have here. So remember, these are the coefficients of your quotient. So since we started with a degree 3, we are now going to have a quotient that starts with 1 degree less. So here's x to the 2 plus 6x plus 8. So we know that our polynomial is equivalent to x minus 1 times x to the 2 plus 6x plus 8. Now, looking at this second bracket, can we further factor it? Because it does ask us to factor fully. Well, I think we can. So these two will factor out to x, 2 and 4 plus. So now that we have broken it down to 3 brackets, I think that is as simplified as we can get. So here we go. This polynomial we had is equivalent to x minus 1, x plus 2, x plus 4. All right, so now that we've looked at a scenario of a polynomial where a coefficient is 1, well, what happens when the leading coefficient is not 1? So here's our example of a polynomial where that leading coefficient is not 1. Remember, this is our leading coefficient. Okay. So look for the possible integers which divided into the constant term. So that's what you'll need to do first. In the constant term, we're looking at 2 as our constant term. So that's 1 and 2. And again, we have plus minus as possibilities. Now we're going to look at the possible integers which dividing into the leading coefficient, which we have labeled here as 3. So that leaves us with 1 or 3. So this is actually what we're going to call A up here, and this is what we're going to call B. So when we're looking at leading coefficient that is not 1, the numbers that we will try in step 2 are actually going to be in the form of A divided by B. So we're just going to try the different combinations here. Okay, so looking at our first example, we have 1 divided by 1, which is just plus, oops, whoa, what happened there? Which is just plus minus 1. Now next we have 1 divided by 3, so that's just plus minus 1 divided by 3. Next we have 2 divided by 1, which is just going to be plus minus 2. And plus minus 2 divided by plus minus 3, whoa, which is just plus minus 2, oops, 2 over 3. So basically what we found up here just kind of talks about the rational zero theorem, where when you have a polynomial function has a rational zero of x equals to a over b, if you have the rational zero, then a is going to be a factor from the constant and b is a factor from the leading coefficient. That's basically when we're building that a over b here, okay? All right. Step 2, find a number that gives the expression a remainder of 0. Very similar to what we did last time. So now that we have these options here, we're just going to pick one. And this time I'm going to pick k equals to -1. So now we're just going to stick it into our polynomial, which I need to scroll back up to remember what it is. So that's 3, -1 to the 3, minus 4, -1 to the 2, minus 5, -1 plus 2. So from here, the same thing as before. So this is going to be -3, minus 4, plus 5, plus 2. So -3 minus 4, that's -7, plus 5 plus 2, that is 0. Yay! So since we have a remainder of 0, what does that tell us? Well, since k is -1, that means x plus 1 is a factor. Now that we found our factor, move on. So now we're just going to do long division again. So again, I'm going to use synthetic division. You can do either or. So the coefficients we're looking at are 3, -4, -5, and 2. And the factor that we have is 1. Bring down the first number. So that's 3. Multiply and put it there. Subtract, -7. Multiply, bring it over. Subtract. This will be plus 2. Multiply, bring it over. Subtract, 0. Remember, this part must be 0. If it's not, as I mentioned before, just double check either the last step or your current division step. So this part means x to the 2 minus 7x plus 2. That is our other factor. So first, we already know x plus 1 is a factor. And 3x squared minus 7x plus 2 is another one. Okay. So from here, can we factor this some more? Why? Yes, we can. So it's always tough when you're looking at that, number, this coefficient here as bigger than 1. So I'm just going to write this out as a refresher. For those of you who can factor this already, then don't worry about it. I'm writing this out just as extra information. Okay, in fact, I'm going to write it in green, kind of off to the side here. So remember, when you're factoring something where that a or that value in front of the quadratic is bigger, where that it's not 1, then you'll need to look for two numbers that multiply to the first and last number here. So in this case, is 6, multiply to 6. And we'll add up to this middle number in the middle. So add up, in this case, to -7. So in this particular case, the numbers we're looking at is -6, -1. These two numbers will give us the combo of multiply to 6 and add up to -7. From there, we're going to take these two numbers and replace that -7. So we have 3x squared minus 6x minus 1x. So added together will give us our -7 plus 2. Now we're just going to kind of break it in half there. And we're going to factor what we can from either side. So from the left side here, we can factor out 3x, which leaves us with x minus 2. And from the right side here, we're going to factor, we'll have to factor out that negative sign too. So it'll be -1 in this case. And we're left with x minus 2. So at this point, you should always have the same thing in the bracket. Again, it's one of those points where if it's not matching, then you know you've done something wrong. So from here, we could factor out our x minus 2. And what, I'm going to move it over a bit. So x minus 2. And then what we're left with is 3x minus 1. So here is the factored form of this kind of quadratic that we had there. So let's rewrite it. So therefore, we know that the factored form is going to be x plus 1, x minus 2, 3x minus 1. This is our final fully factored form. And that is it for this section.